lineup of accomplishments and achievements. He's also an accredited inventor and has 25 patents in the United States, so very impressive. So, Brent, you want to come up? So, Dr. Brent Boss.
Thank you, Chris, for the nice introduction. Good morning, everyone. I'm really happy to be here this morning to talk to you about the Phoenix mission, which was in the middle of its operations last year at this time. And unfortunately, Peter Smith, who was the Phoenix principal investigator, the PI, couldn't be here this morning. He's moving his daughter across the country from Arizona to North Carolina. But he sends his best wishes to you and his regrets for not being here. So I'm going to be talking about Phoenix today. So let's get right into it. What I want to cover is give you a little background on the mission. How did it start? Why did we call it Phoenix? And give you a little background on how it actually came to fruition. And then I will give you some detail on the spacecraft and instruments. That's what I like. I really like the hardware. I like building it. I like sending it to cool places. And so I'm going to go into some detail on that. And then we'll get into the water observations that we made. It actually wasn't that hard to find the water once we got there. There was a lot of concern, particularly as we were planning the mission and traveling there, that we were going to have a very difficult time locating it, that we might have to dig and dig and dig. But you'll see that we saw water kind of everywhere on the surface every time we turned around. And then finally, I'll summarize with how the mission ended and what are some of the most interesting things we learned, and show you some of the results, the most interesting results that we have right now. Okay, so Phoenix was called Phoenix because it rose from the ashes of two missions. One was a failed mission and one was a canceled mission. The failed mission was the Mars Polar Lander, or MPL, and Mars Polar Lander crashed into the Martian South Pole back in December of 1999. Now this, you may remember, was back during NASA's faster, better, cheaper era, and Mars Polar Lander definitely was faster, it was definitely cheaper, it wasn't necessarily better, obviously. And this is a picture of Mars Polar mock-up. That was an engineering mock-up that was in the UCLA test bed, which is where the science operations were based for Mars Polar Lander. After we had the failure, NASA convened a review panel to try to understand why did the mission fail. And there was really, they sort of found the best you can in this business in terms of a smoking gun. They found out that the most likely cause was that the descent thrusters had cut off prematurely, about 131 feet above the surface of Mars. There are 12 of them, 2 of them on each side of the lander legs. You can see these lander legs here. There are 2 of them located on each side of the struts. And what they think happened was that when the lander legs deployed, there was enough force generated from that deployment that it sent a signal to the computer saying, oh, we've touched down, we're on the surface. So when the computer, during the ADL phase, the entry, descent, and landing phase of the mission, started to look for signals that it had touched down on the surface, the very first time it looked, it saw that signal and said, oh, I'm on the surface, let's cut the thrusters off. But unfortunately, we were too high above the surface and most likely crashed to the ground. And this was actually replicated, I think, 3 or 4 out of the 5 times they did this with the engineering test unit here on the ground. And had we done proper testing on the ground ahead of time, we would have found this, even during the cruise phase, and been able to fix this before we landed. There was also a concern that the review panel highlighted, which were with these descent thrusters. Unlike Viking, which was the other soft lander that the U.S. has successfully put on Mars, the Mars Polar Lander had these pulse thrusters, so they could only be turned on and off. They weren't throttleable like the Viking landers. And so there was some concern that this pulsing action may actually cause the spacecraft to be unstable as it was landing as well. But we were pretty sure it was really this strut issue with the sensing, premature sensing of the surface contact. The second mission that Phoenix was based on was this canceled mission, which was the 2001 Mars Surveyor lander. So that's shown here. This is an artist's rendition of the 2001 Mars Surveyor. So after the Failure Review Board came out with their recommendations or their findings, we kind of lost our nerve, at least in my opinion, particularly for the folks of us that were working on this. Even though NASA had already spent more than $100 million on the development of the hardware, kind of lost our nerve because the entry, descent, and landing portions of the spacecraft were essentially a direct copy of the Mars Polar Lander hardware. So even though we thought we had a really good idea and had a smoking gun on what killed Mars Polar Lander, NASA decided not to fly it, and they put all the hardware in bonded stores and its future was really unknown at the time. This was back in 2000, about 6 months after the failure of the Mars Polar Lander. But then, in late summer of 2001, NASA headquarters announced that they were going to make all this 2001 Mars Surveyor hardware that was just sitting on the shelf. They were going to make that available free of charge for Mars Scout missions. So back then, Mars Scout missions were kind of a new concept. It was really the first time NASA was going to do a Mars Scout mission. And the key things with the Mars Scout mission are that one of the key aspects is that it's a principal investigator-led mission. Okay, so instead of kind of a big panel of scientists and engineers and management types at NASA deciding what the goal of the mission is, the principal investigator is responsible for all aspects of a Mars Scout mission. The other thing a Mars Scout mission has to be is it has to be low cost. So in order to be a mission that sort of supplements what's going on in the normal course of Mars exploration, it has to be low cost. You can't spend 10 years and $1 billion trying to build a mission to go off and do your exploration. It has to be relatively cheap. And it also has to be responsive to the latest Mars discoveries. So those are the three key things that Mars Scout missions needed to have. And this was really the first time that NASA was doing a Mars Scout mission. So at that point in time, I was working for Peter Smith. Here's Peter right here. This is him and I up in the Arctic, up in Devon Island in the summer of 2001. And actually, the Mars Society was involved in some of the work we were doing here. We each took a turn doing a rotation at FMARS, that inaugural season up at FMARS. And Mars Society paid to get some of our equipment up there and get ourselves up there as well. So this is actually, we took some of our engineering test unit hardware for cameras and other spaceflight hardware. And in addition to doing the manned Mars simulations, we were doing some unmanned Mars mission simulations as well. This shows the robotic arm digging into the soil up there on Devon. This is a robotic arm camera, the scoop. So when NASA made this announcement, Peter decided to throw his hat into the ring here, which was a little bit late in the game. At this point in time already, there had already been 10 proposal studies funded by NASA given to various teams across the country to go and study their Mars Scout mission concepts and more. So Peter was coming to the game a little bit late, but he had a couple things going for him. For one, he was the Imager for Mars Pathfinder principal investigator, so he had a really good reputation inside the small Mars exploration community. And he had also built 5 other Mars lander imagers, so he had a lot of space flight hardware experience. So Peter put together a proposal, and in August of 2002, he submitted it to NASA. He had the University of Arizona being the lead institution because that was his institution. So University of Arizona was in charge of everything. He delegated project management to JPL, which obviously was a good decision because JPL normally leads our Mars missions. Spacecraft management was given to Lockheed Martin. They were the original fabricators of the 2001 hardware for the spacecraft. And about a year later, August 4th, 2003, Peter was called up by Orlando Figueroa, who's one of my bosses now at NASA Goddard. Called him up and said, congratulations, Phoenix is going to be the first Mars Scout mission. So what did Phoenix have going for it? Besides using all of this hardware that was just sitting on a shelf, not doing anybody any good, the other thing that Phoenix had going for it, in my opinion, was it was very responsive to a recent discovery, a recent Mars discovery that had been made. And this discovery was made from orbit by the Mars Odyssey Gamma Ray Spectrometer. The PI for that was Bill Boynton. And it had discovered what it believed to be a lot of water ice, particularly at high latitude, so at plus 60 and below negative 60 degrees latitude on Mars. This instrument detected a lot of water, roughly 50% by volume. So that's what's shown. This is a map of the water from that instrument shown here. And the blue areas, the dark blue areas, show where it detected high concentrations of water. It wasn't actually, even though it's part of the gamma ray spectrometer experiment, it wasn't actually detected by gamma rays. There was a neutron detector on board, and it detected hydrogen. And the hydrogen was interpreted to be bonded with oxygen. So it was interpreted that this was actually a water ice signal. So Phoenix proposed to fly to the northern latitude region, and our landing site was right about there, so right in one of those sweet spots where there should be lots of water. And this was very exciting because one of the NASA mantras, one of the goals or themes for NASA Mars exploration is follow the water. And you want to follow the water because it gives you your best chance of detecting life. If you're going to look for life on Mars,